Continuing with map projections, it is really important to note that generally there are three major groups or classes of map projections. Initially, we're going to have a cylindrical, a conic, and or an azimuthal. This is also known as a planar map. And so you can see, again, looking at the sheet of paper that is being wrapped around the planet, this is going to be a cylinder that is being wrapped around the planet. We have the line of tangency, meaning that this is where the sheet of paper basically touches the globe. And so the images are being projected from the globe onto this cylindrical map. A cone is exactly what it sounds like, has a point at the top. The point of tangency, meaning where the piece of paper that the map is being projected onto, has a line of tangency that sits right around here, and that is going to be projected and be very accurate for a specific part of the globe, but obviously is not going to cover the entire globe like you would find with a cylindrical map. The final map, the azimuthal or the planar map, has again a single sheet of paper on one side. It still has its tangency. That's again where that quote-unquote sheet of paper is touching Earth's surface. And so you can see that it is going to be very accurate, again, as close or at the tangent point or really close to around that tangent point. And it's going to get really skewed the farther away you get from that. So keep that in mind. All of these different projections have their own strengths. They're always going to be most accurate at the tangent line. And so just keep in mind how each of these projections looks as far as what it takes to create that projection and where its strengths and weaknesses lie. And because every projection is customized to work for the map region by setting specific parameters, it's also important to note that while the majority of maps are going to have one line of tangency, you can have multiple lines of tangency. Again, we'll get into what a standard parallel is in a second, but this is a sectant conic projection, while this is just a single tangent conic projection. And so if you were to take this, it would basically be trying to, or what this is trying to illustrate is that the sheet of paper, the cone that is being separated around the globe, is actually cutting into the globe here. This will be in essence under Earth's surface, and it comes back out of Earth's surface at this line. And so that's why you can see this mild bulging over here on the sides. This is again trying to indicate that this cone, this conic projection, is basically under Earth's surface. So when we're looking at where the most accurate areas are on this map, it's still going to be along this tangent, along this tangent, and the closer we are to these tangencies, the map is going to remain most accurate. And when taking a look at some of these other map parameters, there are a couple terms that you definitely want to become familiar with. The line of longitude that constitutes the central meridian is basically going to be the x equals 0 line on a map. So the central meridian is chosen based on its position near the center of the area that is being mapped. If we're looking at a map of the United States, more or less the center meridian, right, that is going to be the thing that runs up and down, is going to cut through the country basically in half, and that is going to be some random, true random location on the globe. But for the sake of the map of North America, that central meridian is going to more or less cut our map area in half. The standard parallel is similar to the central meridian in that it's going to do more or less the same thing. Using the examples that you can see up here, you can have one standard parallel or multiple standard parallels. And again, this is more or less showing where the main area or the central area of our map exists. The latitude of origin, which is also sometimes called the reference latitude, is the y. And so that is what you're going to need in order to find these standard parallels. And a false easting and a false northing, this is a little bit more confusing. But these are basically arbitrary numbers added into the XY coordinates in order to translate the map to a new location in coordinate space. So while every location, depending on the datum you're using or the map projection, is going to have a predefined X and Y for all of its different data points, you can change the actual location, right, the latitude of origin and the central meridian, giving it a false easting, in essence, moving the numbers in one direction. And the reason that false eastings and false northerns are created is to attempt to get the majority of the map space into positive numbers so that you don't have to deal with any negative numbers. And this is done just so that it is easier to work with the map data. And for the sake of time, I'm going to breeze through the next few slides because I believe you already have a general understanding of map projections. I advise go ahead and pause this, take a look at what I've put up on the PowerPoint, read through this in your book, just to make sure that you're all clear on the difference between a tangent or a secant projection and how that impacts distortion. Also, take a closer look at really what the central meridian as well as the central latitude or the latitude of origin, the reference latitude, actually means as far as our XY coordinate systems are concerned. And also what's good to note is that the orientation of the map, so you can see this is generally the one that we're looking at, when that gets twisted, or I should say when that gets rotated, that is called a transverse cylindrical map. If it is off center, so if it's skewed, it'll be an oblique cylindrical map. Again, if we had that for a conic, it'll still be referred to as a transverse or oblique if it is skewed. We've already discussed how every type of map projection is going to have some sort of distortion attributed to it. Again, there is only one area on the map, on the projected map, that will not be distorted, and that is going to be along what line? You're right, it's the tangent lines. So definitely keep in mind and take a better look at understanding what gets distorted, whether it's the direction, the relationship between different locations on Earth, the shape of, let's say, the continents, depending on how it's being projected. Are they being stretched or are they being squished? The area, does one continent look much larger on a map than it might be in reality? Vice versa, does something look much smaller than it does when you compare it to how it looks on the globe? As well as the relationship between the distances when maps get stretched or condensed. So the distortion will always vary based off of the projection type. So as I mentioned, distortion is inevitable, so the map purpose more or less derives the map projection that you are going to choose. So again, I invite you go ahead and pause this, take a closer look, and again, look into the book. Right now we are around page 116 and read up on the unique differences between these different types of projections. Let's take a look at an example of this. The Universal Transverse Mercator, UTM, is a system based on sextant transverse cylindrical projections, meaning that transverse, it is going to be horizontal lengthwise. Sextant, meaning that it is going to have multiple places that cut through Earth's surface. And again, it's a cylindrical projection, meaning that the piece of paper goes all the way around Earth. The lines of tangency of the cylinder, they fall apart 180 kilometers to each side of the central meridian. So if we're looking at one of these lines, the central meridian of each of these sections runs right down the middle, and there's going to be about 3 degrees to the left and to the right of each of these sections. The total projection includes it includes exactly 60 different zones around the world. And these are areas within a single zone, or I should say the reason that this is done is so that the areas within a single zone have almost no distortion or very little distortion. And so what that does is that preserves all 4 map properties really well. Those 4 properties again are the shape, the direction, the distance, and the area. So looking at these examples, you can see how zone 16 is going to be this 6-degree section that runs from the North Pole to the South Pole. And if we're looking at the contiguous United States, we can see that there are 9 different zones that run across the entire United States. So that's why the UTM is often used for local, county, or small state maps. Because you can comprise an entire state within a single zone, meaning that overall any distortion that is going to be created through projections is going to be very minimal. You should definitely read about the UTM in the textbook because this projection system utilizes false northings and false eastings, and it does a pretty good job explaining as to why we introduced that. So, like I said, definitely take a look at that to gain a little bit more in-depth knowledge on how exactly that works. But let's take a look at another projection. The state plane system, and this is often used for larger scale maps. Again, so that means that our features are even larger, so that really what is happening is that we are zoomed in even further. And so really what this is it more or less uses these north-south zones from the transverse Mercator, as well as the east-west zones from a Lambert conformal conic projection. So again, these are 2 different projections that more or less are getting cut up into even smaller sections. So when this is projected accurately, it's going to minimize the distortion for areas that fit into a single map zone. So other countries have similar systems, but the state plane system for the United States makes sense. It's the state plane system is unique to the United States. And so you'll see too, depending on the area that is being covered, California has multiple state plane systems, while other states are going to have just a singular state plane system. And so basically all that means is that each of these individual state plane systems have a mildly different projection. So if you're taking data from this Northern California, right, California 1, you cannot take data, or I should say the data that you're going to take here, even if it is mapping some data in Southern California, if you try to take the state plane California 1 data and project that on top of the California state plane 5 data, it is not going to match up. There will be some minimal distortion. And why is it important to know the difference between the different ways to project geographic data, as well as the data used to plot that geographic data? Simply put, it has an impact on mapping and more or less how we are displaying our information. And again, as we've talked about, due to the distortion that exists on maps, we have the opportunity, or I should say, it can also hinder us, that different maps, different projections are going to emphasize data and can potentially change what is perceived to be most important. So, infamously, the Mercator projection emphasizes the northern hemisphere and arguably makes the northern hemisphere appear more important, more large than the southern hemisphere. So that is just a simple thing, even when you're looking at your regular world map, to keep that in mind, that the northern hemisphere, or North America specifically, looks like it is much larger than Africa, when in fact Africa is almost twice the size of North America in real life. So when you are looking at projections and when you're deciding what kind of projection you need to use in order to project your data, you should be keeping all of this in mind, right? What is most important? Equal area, equal distance, or relative size. All of these things need to be kept in mind when you are looking at what type of projection you are going to choose to project your data in, as it will tell a different story. And not only can it tell a different story, but it can also impact your ability to analyze data accurately. So the coordinate system used to store the data can impact the result of your data. Areas or distances may be incorrectly calculated. For example, the distance analysis, if you're looking at what is closest, and that is one of the tools that you can run out of the toolbox from the geoprocessing, something that you're all familiar with at this point, even though you've only used it once so far, but that's fine. But the point is that depending on how it is projected, you can see that the data, which is arguably the same data, it's just projected differently, can impact how we might analyze the relationships from certain points to another. So ultimately what this is showing is that depending on how this has been projected, whether it's been the GCS or in UTM, it's showing that the closest, these 3 stars in question, are closest to Hotel C using this projection versus them being closest to Hotel B using this projection. So depending on the analysis that you're doing, again, the projection is going to be crucial to making sure that you are doing everything correctly and, more importantly, accurately. But thankfully, even here, for the most part, ArcGIS Pro has us covered. Thanks to on-the-fly projection, the data that is going to be stored within the coordinate system will automatically be converted to the coordinate system that is being used on the map. So the conversion from one coordinate system to another is not going to affect the data that is actually stored within your data, or I should say the numbers that is stored within each layer. It's only going to change how it is displayed on the map. This obviously makes viewing data much easier as you can bring in data from different coordinate systems, but it is not going to inherently fix any analysis issues. So the on-the-fly projection is going to be able to change the display units. It won't change the actual map units, meaning that your data itself isn't going to change, but it will work in your favor and make sure that if you are pulling in data from a UTM when comparing it to the geographic coordinate system, depending on whatever system you already had up and loaded in your map or whatever you've set it to, it will change the UTM data and, let's say, the state plane data that you are adding to your predetermined GCS data, making the projections on the fly and helping us out as we go. So this image again kind of breaks down the difference between the stored data units versus the display units. So a stored unit is going to be the X and Y values that is stored in a file, and that is not going to change. That is always going to remain in its original or originally set projection. The map units are going to be determined by the coordinate system that is chosen for the map. Again, you can automatic or manually set this. It does automatically set to whatever your first data set is that is being entered into the map. So if you have a blank map and you start with a UTM data set, then everything after that is going to project on the fly to a UTM data set. And that will change, again, the display units, which will default to the map units, which, again, we could change back and forth depending on what we needed. So most importantly to remember here is that the actual data, and this, again, is if you're looking at your map and you can see that here's the little catalog tab. The catalog tab has all of the different data stored in those geodatabases. Those are the files that are .gdb. Where all this data is stored. There's also going to be data stored in those different layer files or those shape files. So that data, those stored units, will never change. But as we are linking how we are viewing the map, right, our display, to that data, the display units are going to be the only things that are changing visually for us. And even though we have talked a lot about the coordinate systems, it is important to note that a coordinate system is only a small part of the actual spatial reference system. The spatial reference system includes the coordinate system, the XY domain, and the resolution. The XY domain is that range of allowable XY values that can be sorted in any feature class. And this range will change depending on how we are storing that data. And so the resolution represents the underlying accuracy of those values. So a resolution of 0.001 meters means that the coordinate values are stored to the nearest thousandth of a meter. And you can find all of this information, the spatial reference information, when you are looking up the coordinate system details. This is something that you can open up, and it also helps to try and read through this and see how much of this you've been able to pick up, whether you're looking at the projected coordinate system, the actual projection that is being used, what is the geographic coordinate system, and so you can slowly and surely make sense of all of these different things that we've talked about that are so crucial to displaying our information on a map, making sure that our data is accurate, and allowing us to conduct spatial analysis. And so ultimately coming back, if you are experiencing issues with the coordinate system, it's because the problems or the data sets don't align when they should. And again, this often happens because coordinate systems or projections are mislabeled, or there is missing or incorrect information. And that is going to display, or I should say inaccurately display our data. So we're taking another look at that map where we had that photo image as well as the road data, where we know that there is a misalignment. And so here they're showing you in the arrows where the misalignment exists of where, this road data should be plotted on top of this imagery data. So again, there's a ton of information here to unpack. Spending the time to go through the textbook is going to be crucial to understanding all of this. And if there are any questions, please feel free to reach out to me. Otherwise, have a good one and get to reading.